Hi, my name is Adam Fraser. I'm the architect for the Sync Gateway component of Couchbase Mobile here at Couchbase. And this session is going to be about getting the most out of Sync Gateway. So I'm going to start off with kind of just a high-level discussion of architecture and performance, but then drill specifically into 4 components of Sync Gateway and talk about how those components work and what configuration and tuning options you might want to think about for those 4 components based on how they're built. So talking first just a little bit about architecture and performance in general. Maybe the obvious question is, do you really need to know all this in order to use Sync Gateway? And the answer is no. Many deployments aren't going to need to dig into these settings. The default settings have been tuned to work for common deployments and use cases. But of course, real-world deployments, they come in all shapes and sizes. So they can vary based on the number of nodes you've got, how beefy those nodes are, but also what your data model is, what your security model is. And from Sync Gateway's perspective, one of its key roles is managing security for your mobile deployment. And so your security model has significantly impacts the performance of Sync Gateway. And then of course, what your edge and your client topology is. So, the number of Couchbase Lite clients you have, if you're running inst-replicate, the number of edge nodes you might be running. And so understanding how some of Sync Gateway's kind of core components work will help you optimize your deployment based on what you know about these factors. So what your data model looks like, what your node count looks like. So let's start by diving into one of Sync Gateway's components, which is what we call import. So first, let's talk about what import actually is. So one of Sync Gateway's roles is to add replication and security metadata to documents to support mobile replication. And so the way a document becomes mobile enabled is that Sync Gateway computes information about what channels that document has been granted access to. So access control information for the document, as well as replication metadata used to build a replication stream for clients. So for documents that are written to the server through Sync Gateway, this gets computed at write time. But for documents that are written directly to Couchbase server, this is computed at import time. So just a quick visualization of what that means. So if you have an incoming document that gets written directly to Sync Gateway, at write time, we're going to run that through the sync function. That's going to compute that document's mobile metadata and write that document to Couchbase server. However, since Sync Gateway 1.5, we've supported shared bucket access, which lets Sync Gateway work with documents that are written directly to Couchbase server. So when a document's written to Couchbase server, Sync Gateway is going to listen to the server's mutation feed and be notified of that document. And at that point, Sync Gateway is going to run the sync function, compute the mobile metadata, and write that document back to the bucket, at which point that document's available to be replicated out to clients. So that process of listening to the server's mutation feed and computing mobile metadata for the document is what we call import. So prior to, in Sync Gateway 2.6 and earlier, import was a single node process. So if looking at your Sync Gateway cluster on the right here, you would identify a single node that would be used for import. That document would be doing all of the work that we described on the previous slide. The rest of the nodes are serving client requests but aren't doing the import work. Now, as of Sync Gateway 2.7, we've enhanced the import process such that the work can be shared across your entire Sync Gateway cluster. So instead of a single mutation stream, your Sync Gateway cluster is listening to a partition mutation stream and sharing the work. So when we say partition, we're actually breaking the server's mutation stream down into a fixed number of partitions. And the number of partitions are what's getting balanced across your Sync Gateway node. So by default, Sync Gateway is running with 16 partitions. So in a 3-node cluster, you'd end up with 5 partitions on 2 of the nodes and 6 on the other. So what's the significance of partitions? So a partition is really just splitting the server's mutations feed. The server has 1024 vbuckets, so that's how the server organizes its data. Those 1024 vbuckets are just split into n partitions. So I think the key piece for thinking about the number of partitions is the last point here. So the amount of parallel processing that we're doing on a sync gateway node depends on partitions. So each partition is worked by a separate Go routine. Sync gateway is written in Go. For those who aren't familiar with Go, a Go routine is Golang's kind of implementation of a lightweight thread. It's not a thread exactly, but it shares some of the similar concepts in that the number of concurrent Go routines that can be getting executed by sync gateway is related to the number of cores that are available on that machine. And that's where the number of partitions becomes interesting. So let's imagine a use case here where we've got 16 partitions distributed across 3 sync gateway nodes. And we want to add another sync gateway node in order to increase the amount of import throughput we can support. Once we add that node, it's going to get registered and be assigned partitions. So the previous 16 partitions are now going to be balanced across all 4 nodes. But you can see here that the overall number of partitions that we're running is not changing. We're still just running 16 partitions. And if those sync gateway nodes have sufficient cores that they could be doing more work, you're not getting as much throughput as you would if you were increasing the number of partitions. And so in a case where you've got a lot more cores available than partitions, increasing the import partitions in sync gateway's config would be a way to better take advantage of those cores. And so whether or not cores are being taken advantage of, it's really just kind of standard node monitoring. So you can monitor the amount of CPU being used on a given node. And if you've got CPU to burn, increasing import partitions is a way to take advantage of that. And you can see the difference here in some of our own internal performance testing. So this is 3 different performance tests that we were running on relatively, well, very beefy machines. So each of them with 48 cores. So running import just on a single node with its 16 partitions is shown on the left. If you split those partitions across 3 nodes, but don't change the number of partitions, you do see an increase in throughput because there's other work being done on the node. But it's not until you actually increase the number of partitions per node, again, because we have a lot of capacity on these nodes for additional throughput because we have 48 cores per node. So as you go to 48 overall partitions, and so you're running with the same 16 partitions per node that you are on the first run, at that point you start to see the kind of 3x throughput. So again, in most cases, the default setting of 16 partitions on, if you're running moderate sized nodes or you don't have a very large cluster, that number is going to be fine. But the ability to kind of tune import partitions as you're working with much larger clusters becomes a good way to get additional throughput from your system. So I think that covers import. The next thing I want to talk about is sync gateway's channel cache. So what is the channel cache exactly? It's an in-memory store of per-channel mutations. So sync gateway has the concept of channels. Its security model is built around channels. So documents are assigned to channels, and then clients are granted access to channels and receive a mutation stream for that channel. And so the channel cache is storing the replication metadata for these channels. It's important to note it's not storing document bodies. It's just some metadata. And it's used to generate these per-channel mutation streams, which are kind of at the core of Couchbase mobile replication. The key kind of features or motivations of the channel cache. The first one is just to reduce query load on Couchbase server. So obviously Couchbase servers, Nickel is very fast, but not so fast that you would want thousands of clients executing the same request for the same data if you didn't have to. And then the second key piece is that it's also streaming per channel mutations to connected clients. So if you have a connected client and sync gateway adds an entry to the channel cache, any connected client gets notified right away. So it avoids clients constantly polling for changes. It acts as the notification system for connected clients. So that's the why. Let's talk about a little bit about what's actually in the channel cache itself. So a given channel cache entry looks like this. You have the document sequence. So this is the order in which the document was written. The document key, its mobile revision ID, some flags. So this is just a bit flag with some information like whether the document is a tombstone, whether the document is in conflict. So again, some metadata that's relevant for replication. And then some information about the time at which this document was cached. So this is a single entry associated with a single server mutation in the channel cache. So the cache for a single channel, so in this case we're talking about channel foo, the cache for a single channel is going to be ordered by sequence. So as you get some mutations being added to the cache as they arrive from the server, those are just going to be added to the channel cache. And so the channel cache is basically a history of the mutations in that channel ordered by sequence. Now, if a client does come and request older data that's not resident in the cache, SyncGateway is going to issue a query for that. And if there's room available in the cache, it's going to prepend those results to the cache. So if a client had come in requesting everything since 0, and the cache was only resident from 105, we're going to issue a query for that data. In this case, we found 4 rows, and we prepended those to the cache. So that's what the cache looks like for a single channel, channel foo in this case. But obviously, SyncGateway can have many channels. And so the channel cache has multiple instances of that per channel history that I was just showing. So since SyncGateway 2.6, clients are only added to the cache when a client replication requests that channel. So initially on startup, SyncGateway's channel cache starts empty, and channels are only added to that cache when a client connects and requests changes for example, channel foo or channel bar. So when thinking about a cache, obviously the interesting piece that you're trying to think about is you're trying to balance the amount of memory that's getting used by that cache with basically to optimize the latency that you're saving by having people use that cache. And so when thinking about the amount of memory associated with a channel cache, you need to think about how things are retained in the cache and how elements are being evicted from the cache. So the channel cache has 2 types of eviction. One is the per channel eviction. So for a given channel, like channel foo, how many mutations are we caching for that channel? And then it also has cross-channel eviction. So this is what's the total number of channels that we're retaining in the cache. So I'll go into detail about each of those, and because there's different tuning options that you can use. And then I'll talk a little bit about at the end about what this means for overall cache sizing. So for per channel eviction, again, we have this picture we saw previously with multiple channels, each channel with a different number of documents in it. So per channel eviction happens at cache update time. So when we're adding a new entry to the cache, we check if the cache has reached its configured limits, and if so, that's the point at which we perform eviction. So per channel eviction, so we're thinking about eviction just for channel foo here, it's determined by 3 values. So we have max length, min length, and expiry seconds. The way this works is the cache is always going to try to maintain at least min length cache entries. So if min length entries have been written to the cache, those are always going to remain resident. When the cache exceeds min length, it's going to retain entries up to expiry seconds until the cache is at max length. So what that means is, for example, with channel foo, by default we'll hold at most 500 entries. But as long as we're greater than min length, those entries are only going to be retained for up to 60 seconds by default. So after 60 seconds, we're going to be evicting those entries to try and get back down to min length. I think a common cache configuration that many customers use is to just to determine, okay, how many entries do I actually want to retain for a given channel, and just set max length and min length to that value. So under that configuration, your max length and min length is really just how many how many entries am I going to store in this channel before I start evicting them? Now, when we're talking about cross-channel eviction, this is done as a high watermark approach. So by default, the channel cache is going to store up to 50,000 channels, but it's going to start evicting channels when it hits the high watermark of 80% of that. So once you have 40,000 channels resident in your cache, compaction is going to kick in, and it's going to attempt to compact the number of channels down to the low watermark. So down to, well, 60% of 50,000 in this case, so down to 30,000. So compaction is based on two criteria. Inactive channels are evicted first. So any channels that do not have connected active replications, meaning there's a client replicating that's connected to this sync gateway node and requesting this channel. So if evicting inactive channels is not sufficient to reach the low watermark, sync gateway does LRU eviction, so least recently used eviction for among active channels. Excuse me. So stepping back, what does that mean for sizing of the channel cache? So as we looked at it earlier, each channel cache entry itself is relatively small. It's only about 120 bytes per entry. This is going to vary a bit based on key length. So if you've got really long document keys, then your cache entry is going to be a little bit longer, but 120 bytes is based on an average, I think, 40 byte size key. It's also important to note that documents that are residing in multiple channels are only stored once. So the maximum memory usage that we're estimating here, that's going to be a little bit smaller if you've got highly shared documents, so documents that are in multiple channels. So an estimate for the maximum memory usage associated with a fully populated channel cache would be max number, so the number of channels that are in the cache, times max length, so the maximum length of each channel, times 120 bytes. So with the default values, if you're looking at 50,000, a value of 50,000 for the number of channels and a value of 500 for the number of entries per channel, you end up with about 3 gig worth of memory if the default value was fully populated. So sync gateway stats provide a lot of information that can be useful for cache tuning. So first, when trying to determine what max length and min length should be set to, I think the obvious criteria is kind of your cache hit ratio. So the channel cache hits and channel cache miss stats can be used to determine that ratio. Also, channel cache max entries is useful to find the number of entries in the most populated single cache. So that gives you kind of like your high watermark of cache utilization. So if you've got a lot of channels of different sizes, you can identify what you need to set your max length to such that your largest channel is fully resident. Alternately, if channel cache max entries is showing up as matching max length, you have some channels that exceed the size of your cache. And then determining max number, so the max number of channels being cached. The channel cache num channels shows the number of active channels. So this tells you whether or not you're hitting max number or not, and whether you're, for that given sync gateway node, whether it's trying to serve more channels that have been requested. And similarly, channel cache compact count tells you the number of times that compaction has been run. So between those two, you can get an idea of whether sync gateway is spending a lot of processing doing cache compaction, and if you have available memory, whether increasing max number is going to give you a benefit or not. And then as far as estimating the overall actual memory usage as opposed to the maximum memory usage we calculated a minute ago, there are 3 stats that can be combined to determine the total number of revisions that are stored in the cache. So we maintain stats for active revisions, removal revisions, and tombstone revisions. And the sum of those 3 is the total number of revisions in the cache. And so adding those 3 and multiplying it by the 120 bytes we talked about earlier will give you a rough estimate of how much memory is being used for the channel cache. So that provides you some guidelines about how to tune the channel cache, which is kind of a key performance determining factor for replication. I think the second one is sync gateway's revision cache. So let's talk about what that's used for. The revision cache, unlike the channel cache, this is storing revision bodies themselves and their associated metadata. So the primary purpose here is short-term caching of recent mutations for immediate replication to connected clients. So your sync gateway, you've got a few hundred clients connected. Mutation comes in that needs to be sent to all those clients. Instead of all of those clients having to fetch that document from the bucket, unmarshal that document to determine its metadata, and then stream it out. It can retrieve all of those replications, can use the shared instance of the document that's loaded into the revision cache. So what's in a revision cache entry? So we have the document key. Again, we have its revision ID. We have the raw body, just as bytes. We have the mobile metadata. So this is what's used for access control and replication. And then optionally, when Delta Sync is enabled, we're also storing a marshaled copy of the document body. And I'll talk a little bit later about why that's needed. But when thinking about what's in a revision cache entry, if you've got Delta Sync enabled, then there's the potential that each entry also stores a marshaled version of that body. So the revision cache is just a simple LRU cache. So again, least recently used. So one aspect of an LRU cache, though, the main benefit of an LRU cache is that it's giving you prioritized eviction. So we're evicting the least recently used element in the cache. But one aspect of an LRU cache is every time there's a read on a document, we need to update that LRU list. And so that maintains obtaining kind of a write lock on that list such that we can update it. Under very high contention, so when you've got a lot of clients concurrently trying to replicate, the work to update the LRU lists can become a performance bottleneck. To minimize that, we've implemented the revision cache as a partition cache. So what we've actually got is a collection of revision cache partitioned by document key hash. And that allows us to maintain smaller LRU caches, or sorry, multiple smaller LRU lists, which reduces mutex contention and increases the amount of concurrent, increases the throughput under high concurrency. So by default, we've got two configurations that you can set for the revision cache. We've got the revision cache size, which defaults to 5,000, and then you've got that shard count. So the number of partitions we've got in the revision cache of 16. So setting revision cache size to 0 disables the revision cache altogether. So if you're in a scenario where you've got very low cache hit, so you've got, that's typically would be in a scenario where you have documents that are not very highly shared. So you might have thousands of clients connected and they're all waiting for mutations, but a given mutation isn't being streamed to very many of those clients. The data set is partitioned per user. If that's the case and you've got very low cache hit, there's an option to just disable the revision cache altogether. In our performance testing, that's only effective when the cache hit rate is very low. So it's only when it's below 10% that 10% or lower that you would want to consider disabling the cache altogether, unless you're very memory constrained. So yeah, based on that, we have monitoring that'll let you identify what your cache hit ratio actually is. So rev cache hits and rev cache misses can be used to identify your cache hit ratio. As with the channel cache, if your cache hit ratio is decent but lower than you'd like it to be, then increasing the cache size is an option based on the memory you have available. As I mentioned, if your cache hit ratio is very low, that's an opportunity to disable the rev cache. When it is disabled, we have a stat rev cache bypass, which tracks the number of rev cache requests that are being served by the bypass by going directly to the bucket. And that's a useful stat just to identify that it's being properly disabled and you're not actually you don't actually have contention on the cache. So in general, num shards shouldn't require tuning. So this is our partitioned LRU cache, and the number of partition is appropriate for the default rev cache size, or increasing the rev cache size by maybe up to double. But if you're increasing the rev cache size quite a bit beyond that, then you're going to start to see degradation based on the number of entries in each partition. So increasing the number of shards, you can get additional throughput if you've got high concurrency scenarios with very large cache, with a very large revision cache. So let's thinking again about sizing and memory usage. So unlike the channel cache, the size of the revision cache is usually dominated by the document body size. So you can expect a given cache entry to be up to 2 times the document body size. So that accounts for both the raw document and the Marshall document that gets used for when Delta Sync's enabled. If Delta Sync's not enabled, you can expect the cache size to be a little bit more than the document body size. So the metadata size that we're storing in the rev cache varies. So it's going to vary depending on your security model. So the number of channels you have assigned to a given document. It's going to vary based on whether your document has attachment metadata or not. But in general, that's going to be less than 500 bytes. So to get a ballpark of your revision cache memory usage, the kind of maximum usage is going to look like revision cache size times 2x of your average document size plus 500 bytes for the metadata. So that'll let you do kind of a back of envelope evaluation of what the revision cache size, how much memory is going to be required for the size of revision cache. So the last thing I wanted to talk a little bit about was Delta Sync. So just as a background of the feature, when Delta Sync's enabled, Sync Gateway has the ability to replicate only what's changed. So the goal here is to reduce the amount of bandwidth between Sync Gateway and clients by only sending what's changed as opposed to the full document. And so the general functionality looks a little like this. You have Couchbase. Consider a scenario where you have Couchbase Lite that's on revision 1, Sync Gateway that's on revision 3 of the same document. Couchbase Lite's going to send a request for revision 3 and specify a delta source of revision 1. So what it's asking here is give me the delta between revision 1 and revision 3 of this document foo. So at this point, Sync Gateway is going to compute the delta between those 2 revisions. It's going to send that delta back to Couchbase Lite, and then Couchbase Lite is going to apply that delta to its local revision. So I think the interesting bit here is probably back a step where Sync Gateway is computing the delta. Obviously, if Sync Gateway is going to compute that delta, it needs to have a copy of that revision 1 available to it in order to compute the delta. And so that leads to the main consideration when thinking about how to tune Delta Sync is that old revision storage. So in order to compute the delta, we need the previous revision, and to increase the availability of the previous revision when Delta Sync's enabled, Sync Gateway can persist a copy of the previous revision to the bucket. So if that previous copy is not being persisted, Sync Gateway is only going to be able to generate a delta when that previous revision is still resident in the rev cache. But by default, when Delta Sync's enabled, we're going to retain revisions based on the value of Delta Sync rev max h seconds. So this is a default of 1 day, which means that when a document is mutated, we make a copy of the previous body, and we store that on the server for up to a day. So any client that comes in and replicates within a day will be able to generate a delta for that document. So functionally, Delta Sync is letting you trade increased storage on the back end for reduced bandwidth. And this is going to have the greatest benefit for highly shared documents, as you pay that storage cost once, but you save that bandwidth every time a client replicates that document. So if you have documents going out to thousands of clients, you're paying for that extra copy once and saving the bandwidth thousands of times. It is important to note, though, that backups are stored per mutation, not per document. And that's to support the fact that with with a mostly disconnected client base like Couchbase Mobile, you can't expect you would expect that different clients are going to be coming in requesting deltas from different revisions. So the previous revision that they have for a given document is just going to depend on the last time they replicated. So what that means is, if you have a highly mutated document, the amount of backups that are being stored is going to be higher, because you can have multiple previous documents being stored for up to a day. So if max age seconds is set to 0, then deltas are only going to be generated when the previous revision is still resident in the cache. So similar to the previous areas of Sync Gateway, we have monitoring that let you get some visibility into how successful your delta cache hit rate is, and whether you want to extend or decrease that rev max age seconds to kind of tune that trade-off between memory usage and save bandwidth. So the key stats you want to look at are deltas requested and deltas sent. This gives you the delta hit rate. So deltas requested is the number of deltas that were requested by Couchbase Lite, and deltas sent was how often Sync Gateway was able to satisfy that request by sending a delta. So if this is lower, than you would like, and you have additional memory, then increasing the delta hit rate can be improved by just increasing the rev max age seconds. So delta cache hit and delta cache miss monitor how many of the sent deltas were served from the revision cache. So this is a slightly different area for optimization, where even if the delta is available on disk, or sorry, in the bucket, we have to go retrieve that, compute the delta, and send it. When we do that, we store it in our revision cache. And so delta served from the cache avoid that kind of processing overhead associated with generating the delta. And so if you're seeing a very low delta cache hit miss ratio, what that means is you may want to increase your revision cache size such that a delta that does get generated remains resident in the cache long enough for multiple users to request it. So I think that covers what I wanted to say about delta sync. And I think that's I tried to give kind of a high level of 4 of the most kind of performance sensitive areas of Sync Gateway. So again, import, replication streaming, replication revision retrieval, and delta sync are kind of, I would say, probably the top 4 as far as performance sensitive operations. And so hopefully from what I've walked through, you get a better idea of how those components actually work and what you can do to get the most out of Sync Gateway for those 4 pieces of functionality. Thanks very much for your time today. Again, I've been Adam Fraser, and yeah, have a good day.